Researchers estimate that roughly 70% of the modern canal routes that carry water into Phoenix, Arizona, a city of 5 million people, follow paths that were not laid out by modern engineers at all. Those routes were originally surveyed and dug by hand over 1,000 years ago by a civilization that had no metal tools, no wheels, no written plans, and no leveling equipment of any kind. And here is the part that should stop you cold. Modern hydraulic engineers, running the numbers through computer models today, find that those ancient canals were built at almost exactly the right gradient to keep water flowing without eroding the channel walls or choking the system with sediment. Not close, not roughly right, remarkably precise, to fractions of a degree, across hundreds of miles of desert terrain. That is not a coincidence. That is engineering. And the story of how it happened is one of the most underrated chapters in all of human history. We tend to think of ancient civilizations in terms of what they lacked. No GPS, no calculus, no steel, no computers. But that framing misses something enormous. The people who built these canal systems did not lack knowledge. They had a completely different kind of knowledge, one that was just as powerful, just as precise, and in some ways more durable than anything we produce today. What they had was time. Generations of watching water move. Generations of understanding soil, slope, and flood. They encoded that knowledge not in textbooks or blueprints, but in the landscape itself. The civilization at the center of this story is called the Hohokam. They lived in the Salt River Valley, the same valley that Phoenix now sits in, from around AD 600 all the way to roughly 1450. That is over 800 years. For context, the United States has existed for about 250. These people were building and managing a sophisticated water infrastructure for longer than America has been a country. At their peak, they maintained over 700 miles of major canals, with some estimates putting the total network, including smaller distribution channels, closer to 1,000 miles. That network watered 256,000 acres of desert farmland across 14 separate irrigation systems and supported a population of around 80,000 people. Now think about what it takes to move water across a flat desert for hundreds of miles. The gradient has to be almost perfect. Too steep and the water accelerates so fast it carves the channel walls apart. You end up with a widening gully, not a canal. Too shallow and the water slows down, drops its sediment load, and silts the channel closed within a season. The sweet spot, the zone where water moves fast enough to carry sediment but slow enough not to scour the walls, requires a slope of somewhere between about 1.4 and 1.6 meters of drop per kilometer of length. That is a drop of less than 2 inches for every 100 feet you travel forward. The Hohokam hit that target consistently across multiple different canal systems. Measurements of their surviving channels show gradients clustering right around 1.45 meters per kilometer. The water velocity they maintained, between 1.5 and 3 feet per second, sits exactly in the range that prevents both erosion and sedimentation at the same time. They held that precision across miles of terrain that looks flat to the naked eye but is actually riddled with tiny variations, subtle ridgelines, and shifts in soil composition that would trip up even a modern survey crew not paying close attention. How? That is the question worth sitting with for a moment. Part of the answer is simpler than you might expect, and part of it is more profound. On the simple side, water itself is a perfect leveling instrument. Fill a long wooden trough or a tube with water, and the surface of that water is, by definition, perfectly horizontal. The ground underneath can be as uneven as it wants. The water surface gives you a true level datum anywhere you plant it. Pair that with a couple of sighting rods and you have a functional surveying tool accurate to fractions of a degree. No manufacturing required. No calibration required. The physics does the calibrating for you. The Hohokam almost certainly used some version of this. But there is a second tool that gets even less credit, and it is the A-frame plumb bob. Take 2 poles of equal length, join them at the top, hang a weighted string from the apex, and mark the center point on a crossbar connecting the legs. When the string bisects that center mark, the frame is level. Build one in an afternoon from wood and a rock, and it works just as reliably as a machine's spirit level. The Romans used versions of this, so did the Egyptians, so did dozens of cultures around the world, completely independently. But here is what neither of those tools fully explains. Tools only work if you know where to put them. The real engineering insight, the one that took generations to develop, was topographic knowledge. The Hohokam did not just read the desert, they understood it the way a ship captain reads ocean currents. Their elders carried mental maps of every ridgeline, every alluvial fan, every place where the ground naturally fell at the right angle to send water where it needed to go. They knew which valley shoulders already carried near-ideal slopes, which meant the engineering problem was not starting from scratch, it was refinement. Reading a landscape that already had the answer written into it, and following that answer with a digging stick. And before they committed to any major channel, they tested. Small pilot channels were dug first, water was sent through. Engineers, and yes, that is exactly the right word for them, watched how the water moved, where it slowed, where it cut, Then the main canal route was adjusted. That iterative process, running over decades and generations, converged on answers very close to what modern computational fluid dynamics arrives at today. Not because ancient people were mystical, because physics does not change. Watch water move carefully enough for long enough and you will learn what water knows. Now here is something that should genuinely unsettle you about Phoenix. When American settlers arrived in the Salt River Valley in the late 1800s and decided to build a canal network to irrigate their new farms, their surveyors fanned out across the desert and began plotting routes. And again they kept finding that the best route, the one the terrain demanded, the one the hydrology pointed toward, was already a trench. An ancient, silted-over, partially collapsed trench left behind by people who had been gone for 400 years. Researchers estimate that roughly 7 out of every 10 miles of canal that Phoenix runs today follow paths originally surveyed and dug by the Hohokam. A city of 5 million people is, in a very real sense, living inside the irrigation blueprint of a civilization that vanished before Columbus sailed. But the Hohokam story does not end with triumph. It ends with a lesson about precision that cuts both ways. Around 1450, after a series of severe mid-14th century floods, possibly the worst the region had seen in centuries, the Salt River permanently dropped its bed. Not by much, but by enough. The river sat lower in its channel than it had before, and that small change cascaded through the entire system. Canals built to draw from a river at a certain level now sat above that level. The intake points no longer functioned. Hundreds of miles of precisely engineered channels, built to exact gradients, maintained for generations, went dead overnight. The very precision that made the system so productive is what made it so fragile. A cruder system, one with more margin and slop built in, might have survived. But the Hohokam had optimized so tightly for the river they knew that when the river changed, there was nothing left to adjust. Within decades, the population dispersed. The canal network fell silent. 400 years of accumulated hydraulic knowledge, held not in any book but in human minds, scattered into the desert. That collapse points to something the engineers of the ancient world understood and we sometimes forget. Knowledge that is not written down is always one generation from extinction. Now pull back from the American Southwest and look at the bigger picture. Because what the Hohokam did was not unique. It was part of a global pattern of indigenous hydraulic engineering that modern archaeology is only beginning to fully document. In the coastal desert of Peru, a culture called the Nazca built something that should not exist. Their landscape is one of the driest places on Earth. Some areas go decades without a single drop of rain. And yet the Nazca built over 40 subterranean aqueducts called puquios, and dozens are still carrying water today, not as museum pieces, as functioning infrastructure. In the 21st century, built around 500 CE, the puquios run underground to prevent evaporation in the brutal desert sun, but the really astonishing part is how the water moves through them. Along the surface, the Nazca cut large spiral openings, some of them 50 feet wide, called ojos, which means eyes. For a long time, archaeologists assumed these were just access points for maintenance. Then researchers looked more carefully at the orientation of those openings and the geometry of the underground channels. Those spirals appear to be engineered to catch the prevailing winds off the Pacific. The wind funnels down into the spiral, builds pressure in the underground channel, and helps push water through the system. A passive pneumatic pump, wind-powered, no moving parts, no fuel. Built over 1,000 years before the industrial age produced anything remotely comparable. Let that breathe for a second. An ancient culture in the Peruvian desert figured out how to use air pressure to help move water underground. And that system is still running today. And then there are the Xenu people of Colombia, who built what may be the largest pre-Columbian agricultural infrastructure in all of South America. Across the San Jorge River floodplain, an area of roughly 1.2 million acres, the Xenu constructed an elaborate network of raised field agriculture and canals over roughly 2,000 years, beginning around 200 BCE. The system managed seasonal floods, drained excess water during wet seasons, held moisture through dry ones, and created microclimates along the raised beds that stretched growing seasons. The whole network is still visible from satellite imagery today, a wetland engineering project close to the size of the state of Delaware, built without any written engineering tradition. Up in the Andes, the Inca were doing something else entirely. Researchers using 3D laser scanning to study the Inca water channels around Machu Picchu, including a 2022 study of the ceremonial water complex at Cochabamba published in the Journal of Archaeological Science, have confirmed what earlier hydraulic surveys of the site found. The main channels were engineered to a gradient close to 3%. That number matters because roughly 3% is close to the threshold that modern hydraulic engineers still use as a guide for where open stone-lined channels start to experience erosion problems. The Inca did not have computer models. They had eyes, water, and generations of trial and error. They landed on almost exactly that number. Meanwhile, the Chimu state on the north coast of Peru, running from roughly AD 900 to 1450, built intervalley canals up to 50 miles long that crossed mountain terrain, linking river valleys that had no natural hydrological connection. Cambridge Archaeological Journal research indicates that the hydraulic engineering knowledge required to plan those canals is comparable to what modern engineers would need to design a contemporary large-scale irrigation system. Physical surveying tools have been excavated from Chimu sites, evidence that systematic instrumentation existed, not just intuition. And none of this was new when the Hohokam were cutting their network. Canal irrigation in the American Southwest goes back 3,000 years, with small channels dated between 1600 and 1400 BC found along the Santa Cruz River floodplain in Arizona. Even in Chaco Canyon, one of the harshest, most water-scarce environments in North America, with no permanent river anywhere nearby, the ancestral Puebloans built canals averaging 15 feet wide and more than 4 feet deep, stone-lined, fed by mesa-top runoff diverted through masonry dams, in a canyon that gets about 9 inches of rain per year. So, what does all of this actually mean? There is a lazy story we tell about technological progress, that it moves in one direction, from primitive to sophisticated, from guesswork to precision, from ignorance to knowledge. The canal builders of the ancient world blow that story apart. What they achieved was not a primitive approximation of modern engineering. It was a parallel and in some ways remarkably competitive solution to the same physical problems. They worked without the error margins that come from ignorance. They worked without those error margins because they had narrowed the ignorance through direct, sustained, multi-generational observation of the physical world. Modern engineers run calculus to find the ideal canal gradient. The Hohokam ran centuries. The Inca ran centuries. The Nazca ran centuries. All of them landed on remarkably similar answers, because the answers were always there, written in the behavior of water, waiting for anyone patient enough to read them. The instrument was not made of brass or glass. The instrument was the human mind applied over generations in direct contact with the land. When you understand that, the real tragedy of the Hohokam collapse is not that they lost their canals, it is that they lost the engineers. 400 years of accumulated, embodied knowledge walked out of that valley and was never fully reconstructed. Think about what that means right now. In 2026, as ancient water systems around the American West buckle under drought and development pressure, the people who laid the blueprint for modern Phoenix spent a millennium learning how to manage water in a desert. Most of that knowledge was never written down. Almost none of it has been fully recovered. It did not vanish because those civilizations were primitive. It vanished because we stopped listening. So here is what I want to know from you. And I mean this as a genuine question, not a throwaway comment prompt. What do you think gets lost when knowledge lives only in people instead of books? The Hohokam case is not a one-time story. There are dozens of civilizations whose engineering traditions survived only as long as the people carrying them did. Drop your answer in the comments. I read every single one, and this is the kind of question where I genuinely want to hear different perspectives. If this video shifted something in how you think about ancient engineering, hit the like button and pass it along to someone who still thinks primitive and ancient mean the same thing, because they really do not. And if you want to keep going down this road, next video we are getting into how ancient civilizations map the stars with nothing but sticks and shadows, and why their measurements were sometimes more accurate than what we produced in the early space age. Make sure you are subscribed so you catch that one the day it drops.